Without any further interruptions, I'm going to get into the content. Okay, so the basic units. The basic unit of all electrostatics is charge, which is written as Q, has the unit of coulombs. Electrons have an elementary charge of -1, as you might know from your general chemistry class, and protons have an elementary charge of +1. But in terms of physics, that's not actually how we consider charge, right? In physics, we consider charge in terms of coulombs. And in physics, an electron has a charge of -1.6 times 10 to the -19 coulombs, right? It's not necessary to memorize this. I doubt they'll be asking you about it, like what the charge of an electron is. They'll usually give it to you. And if you want to know the charge of a proton, it's exactly the same as this, except it's positive 1.6 times 10 to the -19th, right? And most of the time, they won't just be asking about maybe an electron. They'll be asking about some kind of atom, which has multiple electrons and a different charge. But this is just something I wanted you guys to know, that the chemistry definition of charge and the physics definition of charge are very different. They use different units. In chemistry, we use elementary charge, which is -1, -2, -3, +1, +2, +3. In physics, we use coulombs, which is a concrete number instead. Okay. Next, I want to talk about what the electrostatic force is. So if you remember from our force lecture, we talked about mechanical forces. So we talked about tension, normal force, gravity, friction, all of those. So in addition to the mechanical forces, we also have an electrostatic force. And the electrostatic force applies to anything that's electrically charged, any particle that's electrically charged, like say protons, electrons. When we actually consider real physical things, like say me or this pen or a water bottle or whatever, they technically do have electrostatic forces with each other, but most of the time, or most time they do have electrostatic forces, but electrostatic force is so small that it doesn't play a role when you're talking about big things. But when you're talking about small particles like protons, electrons, atoms, and anything like that, then electrostatic force is a big factor, more so than even gravity, right? As I mentioned, everything experiences gravity, right? Even the small particles like electrons, they have some kind of mass and they experience a gravitational force, but because they have such small mass, it's relatively small compared to the electrostatic force, okay? Just like all forces, it's a vector. Electrostatic force is a vector, has a magnitude and a direction. The magnitude of this force is equal to this formula, Fe, which is the electrostatic force, is equal to K, which is Coulomb's constant. And it's a constant, I didn't even put it here because I don't think you should memorize it. They'll always give it to you along with its units, right? Q1, Q2, which are the charges of the two particles that we're looking at. So if we're looking at a proton and an electron, Q1 would be the charge of the proton, Q2 would be the charge of the electron. And all of this over d squared. D is the distance between them. So again, if we're looking at a proton and electron, d would be the distance between the proton and electron in that specific case, okay? If you notice, actually, if you were here for the mechanical force lecture, or if you just remember from your physics class, this is almost exactly the same as the formula for force of gravity. If you remember, force of gravity is Fg equals big G, which was a constant, M1, M2 over R2, right? Where M1 and M2 are masses, and R2 is the distance between the two objects. This time for the electrostatic force instead of the gravity force, we use charge. Q1 and Q2 are charges instead of mass. So Q1 would be the charge of the first atom. Q2 would be the charge of the second atom. Like I said, if we're looking at one proton and one electron, Q1 would be the charge of the proton, Q2 would be the charge of the electron. If we're looking at two electrons, Q1 and Q2 would both be the charge of the electrons. And instead of G, which is the constant for gravity, you use K. K is is Coulomb's constant, right? Because Coulomb was the one who kind of found this out. And like I mentioned, I'm not including it here, but they'll always give you Coulomb's constant in a question or in a passage or anywhere, along with the units. They'll give you the value and the units, right? And they'll always tell you that it's Coulomb's constant. So you don't have to memorize it, okay? And this is the equation to find the magnitude of the electrostatic force between any two charged particles, right? Protons, electrons, atoms, anything that has a charge. The direction of this force is different from what it is for gravity. If you remember, any two objects, no matter what objects or their masses or their sizes or the distance or anything like that, the gravitational force between two objects is always towards each other. So for example, I have this pen and I have myself or my hand right here. My hand and this pen have a gravitational force between them, right? It's very small because very small objects, but there is a gravitational force. The direction of the gravitational force is always towards each other. So from the force of, sorry, the force of my hand onto the pen is towards my hand. So it's going this way where my finger's pointing. From the pen onto my hand is in the opposite way. It's towards the pen. So it's this way, right? It's always towards the other object. However, in electrostatic force, this is not always the case. In electrostatic force, it depends on the charge. If the charges are like or they match, so for example, if both particles have positive forces of positive charges, or if both particles have negative charges, if they're the same charge, the force is actually away from each other, which is not like gravity. So if the pen in my hand were both protons, the force would actually be these ways, right? It would be away from each other, right? It would be a repellent force. However, if they were opposite charges, say a proton and electron, as you may remember, it's towards each other. Okay. All right. I actually want to give you guys the first poll question. It's a little bit early, but just based on what we've been covering so far, with direction and magnitude of electrostatic force. So this uses very simple numbers. Usually you won't see numbers this simple for charges, at least for coulombs, like +2, -5, -1. But this is just so you learn the idea, right? Now I'm going to start a poll, right? There's 4 answer choices, A, B, C, and D. And there's also another option where you really don't know. And the question is, which way will this particle move as a result of these two particles? Will it go this way, where A is pointing? Will it go where B is pointing? Will it go where C is pointing? Will it go where D is pointing? And as a hint, remember to take into account both direction of the two forces and also the magnitude of the forces and how that would affect the vectors. Okay, does that make sense? Okay, I'm going to close the poll. So the most popular answer was A, with B being a close second. C and D were not very popular. However, the correct answer actually is C, right? So let's go over this. So first thing I want you guys to remember is direction, right? And when you see something like this, you would always, first thing you would look at is direction. So the forces being applied onto this middle particle are from these, both of these, right? Because I said anything that's charged is electrostatic force. So what would happen is this is a positively charged and this is a negatively charged, right? So that means the direction of the force would be towards, right? Because they're opposite charges, they attract. So it would be towards. So this one moves towards this +2. So it would be going this way. This one, but it also has an interaction with this one, right? Because they're both negative, -1, and -5, the direction is away because like charges repel, right? What is directly away from this? It would be this way, right? So if I would draw it again, this is the -1 Coulomb particle, has a force going this way and a force going this way. Now we have to add up these forces because forces are vectors, and we have to add them together to get a net force or a total. Again, we break them into components to do this. So you would have an upward component for this one, a leftward component for this one, a downward component for this one, and a leftward component for this one. Now we want to just add together all the components in the same direction. So for example, in the x-plane, we see there's a leftward component and a leftward component. So the net force in the x-plane is leftward. And then we have an upward component and a downward component in the y-plane. So normally this might cancel out. And if it cancels out, you would get something like B. But the y component in the up direction and the y component in the down direction are not equal in magnitude, right? One of them is bigger than the other. What is the magnitude of an electrostatic force determined by? It's determined by Coulomb's constant, which is the same no matter which two particles you look at. So that's not the case. It's determined by distance. They should have, the question actually should have specified that they were equidistant from each other. So 1, -1, so like all three of these are equidistant from each other. So this distance, and this distance are equidistant, meaning that distance wouldn't have been a factor. And lastly, it's the charges themselves, right? Now, if we look at the charges themselves, between these two, it's -1 and +2. When you multiply that together, you get a charge. When you multiply the charges together, you get +2. However, when you multiply this one with this one, you get a charge of -5. Therefore, the one that's -5, or where the charge multiplied to make 5, is actually much greater, right, in terms of magnitude than the force between these two. Because of that, the downward component due to this one is actually slightly greater than the upward component due to this one. So this gets completely canceled out, but this only gets mostly canceled out. There's still a slight downward component. So that means there's still a slight downward component. When you add these two net components together, you get a down left component, which is this way. And that corresponds to answer C. So I want to talk about current now. So current is a measurement which tells us the amount of charge running through a certain point over time, right? It has units of amperes, or A is the symbol, right? And the symbol for current is I. And the other units for amperes is coulombs per second. Because the units are coulombs per second, one equation that we can use to find current is actually I equals Q over T.
Later.
Where Q is charge and T is time, right? If you look at the units for Q is coulombs, unit for T is seconds. So coulombs per second is Q over T, right? This is an important equation that you probably should know. Okay. For current, okay, and just remember amperes are equal to coulombs per second. Remember the units. I can't stress that enough, especially for electrostatics, circuits, and anything like that in physics. Remember the units, right? Units are very important because they'll help you solve problems that you may have forgotten a formula for or something like that. Next is voltage. Voltage can also be defined based on charge. It, however, also uses work or energy. So the units for voltage are volts. Voltage is written as capital V, and volts, the unit, is written as lowercase v. The units for volts are also can be joules per coulomb. Okay. Because of that, we have the equation voltage equals work over charge, or voltage equals energy over charge, right? Again, looking at the units, what joule per coulomb means joules on the top, coulomb on the bottom. Coulomb is equal to charge. Joule is equal to either work has units of joules, or some kind of energy, right? Okay, that's for voltage. Now, and this is why I said units were important. If you just followed where I was going with units for voltage and for current. So remember from one of our previous lectures, we had power. Power had units of watts, and the equation for power was work over time. We can also remember that current equals charge over time, right? Notice how if we do power over current, we can get time in the numerator and time in the denominator. So they cancel out, leaving us with only work over charge, which is equal to V. Let me write that out for you guys, okay? So we know that power is equal to work over time, right? So if we had work over time, okay, and then we multiply, and then we actually, if we divided that by current, right? And you remember that when you divide something, when you divide a fraction, you just multiply and flip it. So it's now time over charge. Right? Now look, time and time cancel out when you multiply these, and you're just left with work over charge, which is W over Q. And now look, when you did power divided by current, you were left with work over charge, which is equal to voltage, right? So this is another important formula to finding voltage is doing power over current. So if you know how many watts some electrical device has, how many watts are running through it, and you also know that the current, the amount of amps running through it, you could find the voltage, right? However, you might not have remembered this on the MCAT. You might not remember this formula, you might not have seen it or something like that. However, if you are given the power, right? If you're given how many watts something is, you'd be able to think, well, what is watts equal to? And you should be able to think on the MCAT, what is watts equal to? Watts is power. Power is work over time. Work over time is joules per second, right? J per second. And you're also given a current. You know, current is equal to Q over S, right? And then from here, you would actually be able to, like I just showed you right now, you actually are able to derive this formula just knowing the units, right? If you know what voltage is equal to, or what a volt is, and a volt is a joule per coulomb, then just having these two units, you'd be able to figure out what a volt, how to find voltage just using these two if you didn't remember this formula, right? And that's what I wrote here in the bottom. Especially for electrostatics, which has a lot of related equations in units. Try and remember what each unit means. Like, for example, an ampere is a coulomb per second. Doing this will make it easy for you to derive a formula like V equals PI on the spot if needed.